Good day. In the previous video, I will have shown you the amounts of different things, and now we're going to talk about them in this PowerPoint. So this is the mole intro. This sheet is not provided, so you do have to copy these things out. And I can't remember, it's probably about 8 slides or so. Not all that packed. So 24.5 liters of hydrogen, 32.06 grams of sulfur, 27 grams of aluminum, 18.02 grams of wawa, 24.5 liters carbon dioxide. You can say, gee, I've seen that number before. 207 grams of plum bum lead, 12.01 grams of carbon, 36.46 grams of table salt or sodium chloride, and 180.18 grams of glucose. Now, if you don't want to write the words for these elements and compounds, of course you can write their formulas. The big question is, what do these samples all have in common? And the answer is staring at you right up here, where it says the mole has something to do with the mole. Now, a mole, of course, is a word that has many meanings, but here you're going to be introduced to the chemistry meaning. Sadly, no sound effects. There might be sound effects, but the song would get me in trouble. But the nice thing, if they come in at this pace, it should be easy to copy. Hopefully you're good at writing out zeros. Okay, the zeros keep coming. So if you're wondering, you're going to write a 602 and followed by 21 zeros. And it's customary to leave a space. Don't use commas, leave a space to create these triplets. So they all contain 602 with 21 zeros, particles. Well, that's an annoying number to write in that form, so it's a good add for scientific notation. But the reason I wrote this out in this form is it tells us that atoms and molecules are extremely, 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 extremely tiny. That's really the message. This is not a number you'll memorize, although you don't have to memorize it, you likely will memorize it because you'll use it a lot. So this massive number is what we use for counting particles. And those particles can be atoms, molecules, formula units, ions. We could use them for counting other things like donuts. But generally we're thinking chemistry. So that is the magic number. Avogadro's number equals 1 mole. Now when you look at this, the way I've written it, it only has 3 sig figs. Some books will go 6.022 and have 4 sig figs, but we'll be fine with 3. So it's named after the famous Italian who studied gases and came up with the mole. So don't get psyched out by it. All it is a counting device, a way of counting things. So you probably know how to count by dozens. 1 dozen of anything is 12 of whatever. So here we had donuts. 3 dozen apples, 36 apples. 3 times 12. If we had a mole of donuts, we'd have 6.02, excuse me, times 10 to the 23rd donuts. That wasn't COVID, by the way. And if we have 3 moles of apples, we just triple that number. So all of a sudden, 6 times 3 is like 18, but we can see we've drawn it. Proper scientific notation, times 1024. So formula units are for ionic compounds. You're used to using molecules for covalent compounds. Now on the first slide, everything I showed you there was representing the volume or a mass of a mole of particles. And those numbers were chosen carefully because for the masses in particular, they would correspond to what you find on the periodic table. So if I have 12.01 grams of carbon, that is 1.00 moles of carbon, and that happens to be 6.02 times 10 to the 23rd atoms of carbon. It's the same amount of material described in three ways: grams, moles, and particles, in this case atoms. If I have water, now I'm looking at a covalent compound. So if I have a mole of wawa, I have 6.02 times 10 to the 23rd molecules of wawa. If I have 709 grams of chlorine, remember it's diatomic, I have 10.0 moles of chlorine. So all that happened was my 23 became a 24, and that is a big honking number. You could count for the rest of your lifetime and not get that number if you could count 1 per second. So your job is figuring out how to convert between these three things. And it's not very difficult. It's simply a recipe. Follow it. And after a while, it should actually make sense why you're doing it. That's the goal. Some of people can't visualize what's going on. They just have to follow the recipe. But if you really think like a particle, like an atom, like a molecule, things should make sense. So those are the conversions we're going to look at very soon. Before we can look at these three types of conversions, we have to deal with something called molar mass and show you how to calculate those things. And it turns out to be very straightforward. I don't think you'll have a problem with it. But mass, we want to be able to go to moles, and if we have moles, we want to be able to go to mass. Turns out to be a one-step process. Moles to particles, particles to moles, again, one step. But if you're going mass to particles, first you have to go to moles. So it's two steps. You go boom, boom, you get the particles, and to go back the other way, particles, boom, boom, and you're back to mass. So that's your intro. May not make full sense, but as time goes on, it's going to be a fabulous world.